Hey there, and welcome to this explainer. If you've ever stared blankly at a complex math formula and wondered how it actually applies to the real, messy world of signal processing, well, you are in exactly the right place. Today, we're taking those abstract mathematical equations and bridging them directly to practical, dynamic concepts. We're going to break down exactly how signals interact, how they relate to one another, and how systems actually process them step by step. You see, it all starts with one really fundamental question. How do we predict the unpredictable? Think about it. When a complex, noisy signal enters a system, how on earth do we know what's going to come out the other side? Well, we answer this by building up some foundational mathematical operations. We're going to look at the mechanics of how signals are blended and compared, which ultimately gives us the superpower to understand exactly how real-world systems behave. Okay, let's dive right into our roadmap. First up, we're decoding convolution. Second, we'll look at correlation to measure similarity. Third, autocorrelation and signal energy. And finally, we'll tie the whole shebang together with linear time invariant systems.
All right, part 1, decoding convolution. Essentially, the math of signal blending.
So the convolution product of two signals, let's call them x of t and y of t, is defined by a very specific integral operation over time. And it creates an entirely new time-dependent signal, z of t. Now, I know the textbook formula, integrating x of tau times y of t minus tau over all time, might look a little intimidating. But honestly, just think of it in plain English as a dynamic sliding and blending. You're basically taking one signal, flipping it around, and sliding it across the other, calculating the overlapping area at every single instant in time. Finding a direct physical equivalent for this can be tricky, sure, but this specific sliding blend is absolutely crucial for characterizing how certain systems work. And visualizing this concept is just brilliant. Imagine you take a simple, flat, rectangular signal, just a constant value over a set period of time, and convolve it with another identical rectangular signal. That mathematical sliding blend actually produces a perfect triangle. It's almost like math magic. As the sliding overlap increases to a peak and then naturally decreases, it perfectly translates that abstract integral into a clean, geometric shape we instantly recognize. Now, before we get too deep, let's quickly lay down the rules of the road for convolution. First, it's commutative, meaning the order doesn't matter at all. It's also distributive over addition. Crucially, if you shift over to the frequency domain using the Fourier transform, that complicated convolution integral magically simplifies into basic multiplication. That is a huge time saver. And finally, what happens if you convolve a signal with a perfectly narrow Dirac impulse? You just get your exact original signal right back. Moving right along to part 2, correlation. This is where we measure similarity. While convolution blends, the correlation function acts kind of like a matchmaker. It measures the resemblance, or the degree of similarity between signals. We've got two main flavors here. Cross-correlation looks at two completely different, deterministic signals to see how much they overlap as they slide past one another. Autocorrelation, on the other hand, is a bit more introspective. It's what happens when a signal is compared strictly to itself. Now, when we measure the resemblance of two totally different shapes, say a constant rectangle and a steadily increasing line, their similarity grows unevenly as they slide past each other. Because of that uneven overlap, it creates a highly skewed asymmetric shape. It's a really clear indicator that the two signals we're comparing are fundamentally different. But here is a massive mathematical plot twist for you. After crunching the integral equations, it turns out that cross-correlation is basically just convolution happening in reverse. Literally. To be exact, the cross-correlation of x and y is just the convolution product of the first signal reversed in time with the second signal, so these two major concepts we've been talking about, convolution and correlation, are deeply and intrinsically linked together. All right, part 3, autocorrelation and signal energy. Now, what's really interesting about autocorrelation is that unlike cross-correlation, it is perfectly symmetric. It's an even function. Because you're comparing a signal strictly to itself, shifting it forward in time produces the exact same resemblance as shifting it backward in time. Plus, we can normalize this property into a coefficient, which neatly bounds our similarity measurement right between -1 and +1. But here's the absolute kicker. The most vital property happens right at the center line. When that time shift, represented by the Greek letter tau, is exactly 0, meaning the signal is perfectly aligned with itself, the autocorrelation equation gives us the exact total energy of the signal. Let me repeat that because it's huge. Evaluating autocorrelation at 0 directly equals the sum of the squared signal, its total energy. Which brings us to our final act, part 4, linear time invariant or LTI systems.
Let's ground ourselves with a super simple visual. Imagine a box. This box represents a real-world system. Let's call it H. It takes an input signal, x of t, processes it through the system H, and spits out an output signal, y of t. Now, so many actual systems in engineering and physics can be modeled by this straightforward little box with a really good degree of accuracy, provided they meet two specific conditions.
Those two golden rules are linearity and time invariance. For a system to be linear, the response to the sum of multiple inputs has to equal the sum of the individual responses to those inputs. Basically, it's perfectly proportional. For a system to be time invariant, delaying the input by a certain amount of time simply delays the output by that exact same amount, without changing the shape of the output at all. The rules of the game don't magically change based on when you start the clock. And here is the ultimate mathematical payoff we've been building towards. If a system meets those two criteria, if it is both linear and time invariant, then the output, y of t, is simply the convolution of the input signal, x of t, and the system itself, h of t. That sliding blending integral we decoded way back at the beginning of this explainer? It's the direct mathematical consequence of a system being LTI. Convolution is literally the magical key to predicting the system's output. So the absolutely crucial point is this. A linear time-invariant system is uniquely characterized by its impulse response because of the very nature of convolution. If you know the system's impulse response, the h of t, you know absolutely everything there is to know about how that system will behave and react to any crazy signal you throw at it.
So how do you actually find that impulse response? Well, you simply hit the system with a Dirac pulse. Remember earlier when we said convolving anything with a Dirac pulse just returns the original function? Because of that, if you feed an LTI system a perfect instantaneous Dirac spike as the input, the output you get is exactly the system's pure impulse response, h of t. It perfectly isolates the fundamental true nature of the system.
We've spent this whole explainer analyzing signals as they slide and blend across the time domain. But here's the thing. Any invariant linear system is also completely characterized by its Fourier transform, which we call the transfer function. So the final question I want to leave you pondering is this. How do all these intricate time domain interactions translate into the frequency domain? How does the transfer function dictate how energy is transmitted across different frequencies? Well, that opens up a whole new, fascinating universe of signal processing. Thanks for learning with me today.